So before I sort of dive into new stuff, does anyone have any questions about the worksheet I gave you guys last class? I know a couple of you touched base with me during the class, but okay. So let's go ahead and move on into section 4.2-ish. Um, where we're going to be talking about exponential functions. And before we get into exponential functions, I want to talk a little bit about exponential properties. Um, so these are properties that should theoretically, in like the statement of the notes and stuff, these are supposed to be reviewed, but I find that they're very, very good to go back over again because they're ones that people tend to sort of forget. Because there's a handful of rules that deal with exponents and how you put them together, right? So let's let x, y, a, and b be real numbers, and let's let a and b be positive. Then we have a handful of properties with exponents. First, we have a product property, which states that the product of two exponents with the same base, b to the x times b to the y, is equal to b to the x plus y. This one, these tend to make a lot of sense when you visualize them as being a integer amount, x and y being an integer amount, because what's x squared times x cubed? Well, that x squared is just x times itself, x times x, right? And x cubed is x times x times x. So that's x times x times x times x times x. It's all multiplication, so the parentheses are unnecessary. So we get 5x's, or x to the power of 5. Again, property that makes sense. You guys have all probably seen it before or used it before, but it's good to just write it down very carefully. Another reason why these are nice to write down carefully is because we're going to see some really, really nice properties for logarithms that are really similar. Okay. After the product property, we have predictably a quotient property, which is that if we take the quotient of two exponents with the same base, b to the x divided by b to the y, we're going to subtract the exponents, b to the x minus y. We also get a power property of exponents. If we have b to the power of x and then we raise that whole thing to the power of y, then we multiply the exponents. Um, Notice that every time we're sort of condensing our exponents, right? We're taking two exponential expressions and we're converting them to one exponential expression. The sort of power um, of the operation decreases. I don't mean power like exponential power, but like in sort of like this real sense, right? Like multiplication is like a stronger version of addition. It's what we get when we repeat addition a bunch of times. So multiplication, the product of two exponents with the same bases, turns into a single exponent with addition instead of multiplication. Quotient, the division turns into subtraction. Um, so so there's the there's a couple of distribution properties. In particular, exponents do distribute over multiplication. A times b to the power of x is a to the x times b to the x. Um, as a note, let's actually even put this in red. a plus b to the power of x is not equal to a to the x plus b to the x. This is false. Okay. So this is probably the most common mistake in all of college algebra. People want to distribute exponents. You see it all the time when you're like, okay, well, x plus 2 squared, that just must be x squared plus 4, right? It's not true. You have to FOIL. And if you've got a plus b to the power of like 27, you have to do a lot of FOILing in order to figure out exactly what that is. There are faster ways of doing it, but in general, it's still a lot of different operations. You have to multiply everything by everything else. So, um, predictably, we get distribution of exponents over division as well. A over b to the power of x is a to the x over b to the x. Some of these properties are a little bit redundant if you consider multiplication and division to actually be the same operation, which in some sense they are. Division is just multiplication by the reciprocal of a number, but since we usually see them as separate operations, this is actually it's nice to see both property. We also get rational exponents potentially. So if we have some, if we have the yth root of b to the power of x, this is equal to b to the power of x over y. Note the square root of x is the second root of x. So square root of x is equal to x to the 1/2 power. X secretly has a first power on it. Anything that doesn't have a power secretly has a first power on it. Any root that doesn't have a number is assumed to be a square root, the second root. Um, this property actually has a lot of sneaky depth to it. Um, and it's one that, for those of you who are planning on going on to a calculus class, it's one that's really, really important to be able to use. It turns out that taking doing calculus with things that have square roots on them is actually kind of tricky, but if you write them as just rational exponents, it's very, very straightforward. So, number 7, we have an identity property, which is that anytime we have b to the power of 1, that's just b. So if you raise anything to the first power, you get itself back. Pretty self-explanatory. And finally, we have what's called an annihilator property, which I think is way too cool of a name for something as lame as a mathematical property, but I don't know. Anything to the power of 0 is 1. Except for 0. 0 to the power of 0 is a confusing situation that we don't want to talk about. The 0 to the power of 0 has relatively equal claims to being 0 and to being 1, so we usually pick one or the other depending on the field we're in. Combinatorics, which is a fancy way of saying counting, usually for them 0 to the power of 0 wants to be 1, whereas in analysis-based or calculus-based fields, we usually have to be a little bit more careful and figure out what 0 to the power of 0 actually is, because it could actually be anything. It could be 12. It's a mess. So we shouldn't see very many 0 to the power of zeros. And then one more property. This is rolled up into some of the other properties, but it's important. If we have um, 1 divided by b to the power of x, that's, we can rewrite that as b to the negative x. This property follows directly from the quotient property of exponents, b to the x over b to the y. This is 1 over b to the x is just b to the 0 divided by b to the x, which is b to the 0 minus x, which is b to the negative x. Um, we can use these properties to rewrite exponential expressions. It's not something I'm going to be focusing on this class, but it is something that I'm going to assume that you are able to do. So for example, we could rewrite x cubed y squared over the square root of x y to the fourth using rational exponents without or let's say on a single line. Well, we sort of have two parts of this. We have x cubed y squared over the square root of x y fourth. We have the x parts and the y parts. So if we separate those out, we get x cubed over the square root of x times y squared over y to the fourth. X cubed over the square root of x, that's also x cubed over x to the 1/2. We're using the rational exponents property here, number 6. And then y squared over y to the fourth is y to the 2 minus 4. This is the quotient property, number 2. We can also use the quotient property on the x's, giving us x to the 3 minus 1 over 2 times y to the power of negative 2. And 3 minus 1/2 is 5 over 2. And that's written on one line exactly. It's also possible to go back and do this the other direction, to rewrite it using radical notation instead. So. Any questions about these properties of exponents? All right.
Could you write it as x to the 2.5, or does that just...
I mean, it's technically not wrong, but it loses. So the rational exponents are nice because x to the 5 over 2 is very clearly the square root of x to the 5th. Well, it's not super clear, but it is that rational exponent. A rational number translates really obviously to that. Something like x to the power of 2.5 is the same exact thing as that, right? But what the heck is x to the power of pi? Like, what does that have to? What does that mean? Like, what is the pith power of anything? And it turns out that that's actually that's a it is something that is well defined. It does mean something. What does it mean exactly is something that's beyond the scope of our class. It's approximately exactly what you would expect it to mean. It's something around x to the power of 22 over 7 or something like that. Um, but it's not 100% obvious how to write a decimal as a radical form, if that makes sense.
Yeah, yeah, makes sense.
I'm not going to grade you off for saying it's x to the 2.5. Just as a math person, I need to fight for the fractions, I guess. I am the math teacher and I speak for the fractions, like a Lorax. All right, so these rational exponents and exponential properties are going to just be useful to keep in the back of our mind. But really, the key thrust of this unit is more to do with exponential functions and logarithms. So, um, I there are a handful of different ways to deal with exponential functions. Um, in particular, one of the obvious applications of um, exponential functions is compound interest. Well, let's talk about what an exponential function is first. So we've dealt with a lot of exponents, but they've never been variables inside the exponents. The exponents have always had constants inside of them. Um, so exponential functions are functions. So they're functions, which means they follow the definition of a function, just like everything that we've studied so far this semester. They are functions where the independent variable is contained in an exponent. For example, f of x equals 2 to the power of x is an exponential function. And exponential functions actually, we can sort of get an idea for what they look like by maybe taking a table of values and then graphing the exponential function. So let's go ahead and make a table. Let's start with x and y, or x and 2 to the power of x. So let's start with 0. 2 to the power of 0 is 1, because anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4, that's 2 squared. 2 to the power of 3 is 2 cubed, which is 8. And 2 to the power of 4 is 2 to the 16th, right? And if we go in the other direction, 2 to the power of negative 1, well, 2 to the power of negative 1 is 1 over 2 to the 1, which is 1 half. 2 to the power of negative 2 is 1 over 2 squared, which is 1/4. And then negative 3 will be 1/8. Okay. All right. So there's our x-axis. That's 1, that's 2, that's 3, that's 4. Negative 1, negative 2, negative 3. And we'll do our y-axis in ones. So we get the point 0, comma 1. We get the point 1 comma 2. We get the point 2 comma 4. We get the point 3 comma 8. And then we get the point 4 comma 16, which is up here somewhere actually. Negative 1 1/2, negative 2 1/4, and negative 3 1/8. So we end up with our graph looking something like that. Okay. So this is f of x equals 2 to the power of x. And just for the sake of verifying, when we graph it on Desmos up there, we get basically the same picture. So, that. Exponential growth functions, all exponential functions have some commonalities. So exponential functions f of x equals b to the x will always have the point b comma 0, or sorry, 0 comma 1, and the point 1 comma b. These come from our annihilator and our identity property, respectively, right? Anything to the power of 0 is 1, and anything to the power of 1 is just itself. They should also have a horizontal asymptote. On one side. As x gets very, very small, as it approaches negative infinity, b to the power of x will approach 0. Obviously, if you shift your exponential function around, if you move it up or move it down, by using shifts and stretches and stuff like that, like the stuff we did in section 2.6, right? Then that's going to change where your asymptote is. If you move it up, the asymptote will move up, right? If you move it up by 2, the asymptote will be at 2 instead of 0. But it still has that horizontal asymptote. Exponential functions have this limiting behavior. And additionally, on the other side, as x approaches infinity, b to the power of x approaches infinity, and quickly. So there's a famous story or parable about exponential growth that's commonly told, and it usually has to do with the invention of chess. I think the first time that it was recorded was in 1258, and basically, this guy invents the game of chess, and he takes it to the king of his city, and or city or country or whatever, and usually it's India, because that's where chess was invented. And he shows him the game, and he offers to sell him the game. And the king says, "Okay, this game is amazing. I love it so much. Name your price." And the person who invents chess says, "Okay, well, what I want is um, I want 1 grain of rice on the first square of this chessboard. And then I want 2 grains of rice on the next square, and then 4 grains of rice on the next square, and then 8 grains of rice on the next square, etc., etc., etc. Just double the amount of rice every single time." And the king says, "Okay, that's great, fantastic, let's do that. That's deal." Um, and so they start doing that, right? So they get a chessboard, and a chessboard is an 8 by 8 grid. Not going to draw an entire chessboard because it's going to be apparent why this is insane relatively quickly. And on the first square, he puts 1 grain of rice. And on the second square, he puts 2 grains of rice, and then 4, and then 8, and then 16, and then 32, and then 64, 128, 256, 512, 1024, 2048, and it's starting to get out of hand at this point a little bit, right? I mean, 1,000 grains of rice is not actually that much. 4096, 8192, 16384, etc., etc., etc. And it turns out that if you do this for a while, then the growth ends up looking like this. So by the time you get to um, by the time you get halfway down the chessboard, this 2G, it stands for the SI prefix 2 billion. So you have 2 billion grains of rice on the 32nd square. And the last square of the chessboard is in quintillions, I believe. So it's, yeah, 9 quintillion 223 quadrillion 372 trillion 36 billion 854 million, etc. It's an incredibly large number, right? And what happens to this king varies on the story. In a handful of stories, the king laughs it off and he's promoted to be a high-ranking advisor for being so clever. And in the other handful of stories, he's executed. So, depending on what your view of the universe is, probably shapes which one of those stories you believe more. Both of them are probably true, well and truly apocryphal and never actually happened. But hey, it's a fun story. But in general, exponential growth gets out of hand eventually. We'll see more examples of this later. I think Carl Sagan was famously on record as saying, like, you can't just use exponential models for things because at some point, if real exponential growth actually existed in the universe, then it would crush everything else. There's no such thing as actual exponential growth. There's always some sort of limiting factor, which it turns out there is, and we'll discuss some ways to get around dealing with that when we talk about exponential modeling. Um, so going back to the exponential function real quick, a couple of quick properties that I should mention. The domain is all real numbers. You can put anything in an exponent and it works out just fine. Again, I'm not super happy with x to the power of pi being something that's well defined, but it actually is something that's well defined. It is where you would expect it to be. We get this nice continuous interpolation. For instance, if we do x equals pi on our Desmos graph here, we can look and we can see our intersection here. It's 2 to the power of pi is around 8.825, somewhere between 2 to the power of 3 and 2 to the power of 4. And the range is 0 to infinity. If you have a number to the power, if you have a positive number and you raise it to a power, that number will still always be positive. It's never ever negative. Okay, so no matter what you're plugging in there, you should always get positive numbers. Obviously, shifts and reflections and stuff change this domain and range, but for just basic exponential functions, b to the power of something, we have the range 0 to infinity. So one really nice place to use exponential functions is in computing compound interest. It's the one that's probably the most likely for you to actually deal with in your life, and you've probably already dealt with it in a lot of different ways. If any of you are taking out loans for school, you have compound interest on those loans, and eventually they'll start accruing interest. So I can't remember. I'm pretty sure that most student loans accrue interest while you're still in school. Maybe the subsidized ones don't. Regardless, um, we have a handful of different ways of computing compound interest, and the first one is simple interest, which is not actually something that anybody uses for anything. Nobody uses simple interest unless it's like a really small thing on the side, right? So the amount of for simple interest is not actually an exponential function. It's I is equal to P times R times T, where P is the principal amount or initial amount. R is the APR as a decimal, and T is the number of years. So simple interest is it's annoying for a handful of different reasons. First off, because it's the only one of our interest functions that's actually going to give us an interest amount rather than what's called an annuity. And also because again, it's not particularly helpful. This doesn't show up. This is basically saying like we're going to be charging you interest only on the initial amount. It's not going to compound, which because people are greedy and banks want more money, the obvious answer is to say, let's compound interest based on the amount that's currently there, not the amount that you started with. The only reason I even bring up this formula is because just in case one of the homework problems asks you for simple interest, I think I tried to avoid any of the problems that had simple interest, but just in case one does show up, this is how you answer the problem. For compound interest, um, we have the type of compound interest that we typically find, which is periodic compounding interest. When I say periodic compounding interest, I mean that it's compounding interest that compounds every blank period. In a lot of situations, this is typically monthly compounding interest. Sometimes you see quarterly compounding interest. Sometimes you see yearly compounding interest. But basically, it's how long does it take to compound. And compound interest can be written as A is equal to P times 1 plus r over n to the power of nt, where, again, p is the principal, p, r, and t are the same as before. But n is the number of compounding periods per year. So, for example, monthly compounding interest is n equals 12. So, for example, you invest $10,000 in a savings account where you good lord, get 0.99% APR compounded monthly. After 20 years, how much is in the account? 40 years? 60 years? So to answer these questions, we should set up our exponential growth model. And to do that, we're going to use this compound interest periodic function. Our annuity, stands for annuity. It means the total amount in the account after blank days. So our annuity A is equal to the principal amount, 10,000, times 1 plus R. So R is going to be equal to 0.0099. We want to write APR as a decimal rather than as a percent. So we're going to divide 0.99 by 100. So 1 plus 0.0099 divided by 12. Since it's monthly compounding interest, we get 12 periods per year to the power of 12t. So what's a of 20? Well, that'll be what we get when we plug in 20. And let's go ahead and plug that into a calculator. So that'll be, oh, that didn't work. So after 20 years, you'll have $12,188.63. What if we go up to 40 years? Then we'll have $14,856 and $0.27. And then if we go out to 60 years, we have $18,000. The growth between 0 and 20 years was about $2,200. The growth between 20 and 40 years was about $2,700. And then the growth between 40 and 60 years was like $3,500, right? The later into your investment that you are, the faster your investment grows. Whenever I'm sure that in some sort of situation, someone has told you to start saving for your retirement as soon as you humanly possibly can. And that's because of this. When you start saving early, what you're really earning is you're earning those last few years on your investment. And those last few years have the biggest gain, right? If you start investing in your retirement at the age of 18 and you intend to retire at 58 or 60, right? You're getting those last few years. Whereas if you started to invest at 28, that 10 years on the end is what you're really missing. You're missing the largest amount of growth, not the earliest amount of growth. Okay, so you really do want to be saving as early as possible. Of course, it's 2020, so no one under the age of 18 right now will ever own property, and no one should ever save for anything because the whole world's going to end anyway. So what does it matter? But maybe you're more optimistic than I am. I'm not actually that pessimistic, but sometimes I feel. Any questions about compound interest stuff so far? It's relatively straightforward. It'll get a little bit more complicated once we start um, using logarithms, but it's pretty much just using this formula. There is another compound interest formula, but in order to talk about it, we have to figure out we have to talk about something else first. We have to talk about a new fundamental constant. So let's talk about Euler's number. E. Um, so there is this mathematician. His name is Euler. It looks like it's pronounced Euler. It's not Euler. It's Euler. And he did just a ton of math. Like a lot of the things that we teach today, a lot of modern mathematics is essentially based on his foundations. So he was Euler was a mathematician in, I believe, the the 16th century. He was alive from 1707 to 1783. Um, and he was super influential in a ton of different fields. And there's a lot of things that are named after him. There are so many things that are named after him that you actually we stopped naming things after him because we there were too many things at some point, and we started naming them after different people instead. Um, so one of the important ones here is Euler's number, E. And there aren't not a lot of other people that have numbers named after them, especially not numbers that are um, so common as this one. All right, but E is it's a special number. It's somewhere between 2 and 3, but it's really important because it comes from it's sort of a natural base for exponents. It's a base for exponents that makes a lot of things very nice. And one of the ways that it shows up is in compound interest. So let's say, for example, suppose you invest um, $1 at an APR of 100%. This is never going to actually happen, but it's going to make the number I want to pop out, so we're going to try that. All right. Then our compound interest equation, A of t, ends up being 1 times 1 plus 1 over n to the power of nt. And let's suppose we're doing this for 1 year. So that'll be n times 1. We can get rid of a couple of these ones and rewrite this as 1 plus 1 over n to the power of n. Okay? And compound interest, the faster you can compound it, the more money you're going to make. Okay? So how much will you have if you compound annually? Well, this one's pretty easy to check, actually. That'll be 1 plus 1 over 1 to the power of 1, which is 2 to the power of 1. 1 plus 1 over 1 is 1 plus 1, which is 2. And that's just 2. So you'll have $2 after 1 year. What about monthly? Well, we're probably going to need to get the calculator out. That'll be 1 plus 1 over 12 to the power of 12. So let's actually... So when n is 1, that ends up being 2. When n is 12, it's monthly. This ends up being 2.613. Which is more, right? We've definitely increased. How much have we increased by? Well, actually a pretty significant amount, right? We've gone from a $1 return to a $1.60 return, which is a pretty big increase. It's like a 60% increase on our return. So, what if we go to daily? Or let's do weekly first. If we compound weekly, then that's 52 compounding periods per year. 1 plus 1 over 52 to the power of 52 ends up being about 2.693 dollars. And this is better, but it's not as much better. This isn't as dramatic of an increase, right? So what about daily? Well, that would be 365. Which ends up being about 2.7146 dollars. So it's increased again, but very, very little at this point. What if we do it hourly? So there are 8,760 hours in a year. So that's 1 plus 1 over 8760 to the power of 8760 is equal to $2.71813. And just for the sake of being absolutely absurd, what about minutely? There are 525,600 minutes in a year, which I remember because of the musical Rent. And if we plug in 525,600, we end up with about $2.71828. And if we get even bigger than this, if we let n be tremendously large, let's say like we just keep adding. Whoop! I broke Desmos there. Actually, I broke Desmos before that. There we go. This does end up having a limiting factor. Um, and it turns out that there is a limit to how much money you can make by decreasing the period. So if you just increase the number of compounding periods per year, eventually you see a lot of limited returns. So um, by increasing the number of periods per year. And it ends up being something that approaches this exercise yields E. So if as n goes up to infinity, that expression 1 plus 1 over n to the power of n approaches E. This is actually, in many sources, this is the definition of Euler's constant. Um, if we just type E in there, you see that this number, as n got very, very large, is extremely close to what E is. Right? And that gives us our last version of compound interest, which is continuously compounding interest. And that'll eventually bring us into our general idea for exponential models. So continuously compounding interest, often it's used as an approximation because it's actually quicker to compute with, and it's easier to do some application with this version of the formula rather than the normal compound interest formula. But continually compounding interest is a of t is equal to p times e to the rt, where p is, of course, as usual, the principal or initial amount. R is the APR as a decimal, and T is number of years, and E is Euler's constant. .18 or 2.71828 dot dot dot. It doesn't actually repeat. It does it twice, 1828, 1828, and then it goes and does other stuff for a while. It's so E is an irrational number. It's like pi, actually. It's like pi in a lot of different ways. So you, in the same way that you want to know that pi is somewhere around 3.14, you probably want to know that E is somewhere around 2.718, 2.72 ish. You don't need to know exactly what it is. Your calculator will tell you what it is for the most part. Um, so let's take our previous example. You are investing $10,000 in an account with 0.0099, or sorry, 0.99, 0.99% APR, compounded continuously. How much is in the account after 20 years? Well, that would be A of t. A of t is equal to 10,000 times e to the 0.0099 t. And if we plug that into our calculator, A of 20 ends up being 12,189.62 dollars, which is just a tiny little bit more than what we got when we were compounded monthly. Um, it's like one. It's exactly, almost exactly $1 more, 99 cents more. So that's why it's commonly used as an estimator, because it is a pretty close result. Eventually, this will always be larger than your periodic compound interest, however. Okay, so that I believe will be it for today. I am going to leave the lecture there. Does anybody have any questions before I let you guys go? Okay. I will post some questions um, to our Discord channel for you guys to work on, and I will be kicking around. I'll probably be in voice one for the next hour or so. So if you have any questions on either the homework or the problems that you're working on, or the problems that I post, then go ahead and give me a shout in that channel.